Today I'm going to talk about modeling, sensing, and control of deformable robots and an application for building a haptic device. So usually when I present the team, I say, well, we are in Lille, located in between London, Paris, and Brussels. But I guess that if you are here, probably it's because you know where is Lille. So the team is here. All the work I will present is, of course, made by a participant of the team. It's not my work, but a teamwork. The challenge of Defrost is to focus on modeling, simulation and control of soft robots. So when we started the team, we showed this slide where when we start with articulated rigid system, you have a limited number of articulation. Usually you avoid collision with the environment, and you have a well-established method of control. But when you go to deformable robots, soft robots, you don't have anymore the analytical models. You want the robot to interact with the environment, so you need to take into account the interaction model. And of course, for the control methods, it's still an open challenge for the community. So here's my first soft robot. Sorry, so the video will be a little bit slow because we had to go through Zoom to display the video. But it goes a little bit faster than this in reality. So there are four cables and a deformable structure made of silicon. And basically, this work was about to show that for modeling such a robot, we can use finite element method computed in real time. So basically, you take a sample of the material, of the silicon material. You can perform some tests, and then you build a FEM model. And we developed in the team some techniques to fasten the simulation of FEM to make it real time. So basically, when you write this FEM model, you end up with a system of equation. So here is the second Newton law, so the classical Newton law, except instead of as you have to follow the Newton's law at each nodes of your mesh, of course you have a lot of lines. You have to imagine that this non-linear equations. And so basically the FEM model allows to fill the force vector. And if you consider the dynamics, of course you have the mass and acceleration. But today I will more focus on quasi-static to simplify. And an important part is the pulling force on the cables appears as a Lagrange multiplier, as well as the force we apply on the effector. Basically, when you want to compute that in quasi-static, you have several steps in which you linearize the non-linear force to obtain the tangent matrix, and then you solve at each step a big matrix system. And that's all you have to follow, because I will talk a little bit about mass at the beginning. So to start with a little bit of equations, but it will be not too complex, I think. It's just you have to recall that we have a matrix system Ix equal B to solve at each step, plus the Lagrange multiplier. And if we have some pulling force, like a cable, in fact, you have two cases. Either you know the force you pull on the cable, and you know the value of your Lagrange multiplier, and then you can solve the equation. Either you don't know the value. For instance, if you are imposing a displacement, you don't know what force you are applying on the model. So in that case, you have to solve a system like I show here. You don't know the value of lambda A, but you know that on a cable you can only pull. So this lambda A needs to be positive. And basically, you can only pull if your cable is tightened. That's why there is a complementarity at the last equation. It means that either lambda is 0, either when it's not 0, then the second equation is equal to 0. Okay. And basically, all the thing of is to be able to use such a model to control the robot. So what we want to do is to impose a desired motion on the end effector and find how much to actuate to follow this motion. And basically, to do that, we will use what we call the compliance projected in a constraint space. So it's basically you are projecting the A matrix, but not the A matrix, the A-1 matrix, so the inverse of the matrix. So again, this A matrix is homogeneous to a stiffness. So as you are inverting it, you are mechanical compliance, and you are looking at this compliance in a restricted space. So basically, for instance, this matrix, in that case, corresponds to when we put the force on the cable. Okay, here we are able to output the displacement we obtain on the end effector. So here it's a 4x3 matrix. So you start with the A minus, but you really restrict to all the nodes that are of interest for you. And thanks to that, to this relationship, we have a very small system that links the force you put on the cables to the displacement you have at the end effector. Okay, and for the following, what is very important is this W matrix, this idea of having an idea through the model of the compliance of the system, so the coupling between actuator and effector. So it's basically the smallest possible equation system that includes all the FEM model, because we inverse all the A matrix. And when we have this matrix, to compute the inverse model, we can optimize a very small QP, which basically says that we want to minimize the end effector position to the desired position of this end effector. And you can write it like that. And when you have done that, then you can use your simulation to drive the robot. So here, basically, the user is moving the end effector position on the real-time simulation, and the simulation and the inverse simulation compute how much to pull on the cable so that the robot goes to the desired position. Thanks to this, again, this compliance projected in its constraint space, we can do other things. One of them is to use the soft robot as a force sensor, because as the robot deforms, if you observe how much it deforms, then you can find out how much force you have put on it, particularly if you have a good model of the robot. So basically, in nature, there is no force sensor. There's only a deformation sensor. You can only, in fact, measure deformation and find the force. And so here, the basic is that we will create new constraints, not only actuator constraints, but we will put some constraints on some points where we are able to measure the real position on the robot. So we will put some marker point on the robot, and we will measure the difference between the real marker point position and the marker point in the simulation. And basically, what you want to do is to minimize the distance between the marker point in reality and the marker point in the model. And at the end, it's the same thing. You can write a small QP, a small quadratic programming problem. And the advantage, again, of this compliance is that it's still quite reduced matrix. And thanks to that, so here you see the 4 marker point on the robot, on the real robot. And you will see that so we have defined some place where the user can interact, several places, and the simulation is able to find the location where the user is. The intensity of the force is applying on the robot. We have all the ingredients to do a haptic device with that. We are able to measure the force without force sensor. And we are able to drive the robot on a given direction. And we are able to do a QP optimization based on small matrix system. So it's quite easy. The only problem we have is that the time to compute this compliance matrix is time consuming. But the good thing is that we have a good temporal coherency, meaning that this matrix is not changing a lot over time. And the second problem is the mass ratio, the mass stiffness ratio that I've used in these soft robots. So it could create some vibration on the robot. And now I will present a work that we've done with Alison, the team of Alison Okamura on creating a device based on the technology I've shown before. So basically, this device is much lighter. And it's in input and 5 DOF in output. So 3 translation and 2 rotation. And basically, instead of using volumetric finite element method, we are using beam element method because the structure is more modes, but it is the same thing. Okay, here we have a beam force. Instead of the Lagrange multiplier, instead of having cable, we directly put some torque on the curve and we are able to not go into too much detail, but here is to show how we can couple the actuator torque to the mechanical structure. But at the end, you can end up with the same system. But just this equation are just to show that. And we have put some flex sensor on the device, meaning that we are able to measure basically the curvature of each leg, thanks to a new Lagrange multiplier. And thanks to that, if you look at this video, I hope it's and we can really measure the handle just based on the motor rotation and the deformation of the structure. When we did a measurement, basically, so maybe I can explain a little bit. So in fact, we create some constraints to limit the error between the model and the sensor position, so the curvature. We also try to minimize the error between the model and the encoder. Okay, so we have, in fact, we minimize and we obtain a quadratic programming problem. So thanks to that, we can estimate the force and the motion of the end effector. If we look at what we can measure in terms of displacement, here and we compare to the output of SOFA. I don't see if you see the curve, but they are really very close to each other. So meaning that we can find with the minimization the force to apply on the force that the user is applying on the handle. And thanks to this force, we can reconstruct the displacement of the end effector. And also, we did also some tests with basically a robot where we have a real force sensor. So the robot is moving and compare basically the force computed by SOFA and the real robot. So the force that is computed with and it matches quite well, meaning that we are really able to measure the force applied by the user on without any force sensor. So now the last thing that we need to do is to be able to basically what we do is that we have developed a multi-rate approach where we have with the step I showed, but here in the low rate, we compute shared with a high rate loop. Thanks to the fact that there is a good temporal coherency of this between the 10 loops of this high rate, it doesn't change so much in this. So meaning that we can really have a good estimation of the compliance in these high rate loops. And in the high rate loops, we estimate, given the new value of the sensor and the encoder, we can estimate the new error between the model and estimate a new effector state, both force and position. And in step 2, we apply the virtual environment. So if we are the two states, the concept, the force that the user is applying. And then when we have a new direction of motion, we apply the inverse model. Same the 3 steps. First step, in fact, we estimate the force on the handle. Second step, we apply the virtual environment. So if we are in 3 steps, then when we have this new desired motion, we apply it on the robot. And we can do that very, very fast, thanks to the fact that we have used this multi-rate. Two examples where we have used these two. So here the thing we want to simulate is just a circle. So basically, when the user is the haptic will try to put you back on the circle. It's a little bit too loud now. Sorry, can you? It's okay for you, or is it? It's okay. Okay. So basically, you see that on the graph, you see the user position in blue, and in red, you see the desired circle, like the virtual environment. So of course, it's a simple virtual environment, but still we show that we are able to follow this trajectory. And as here in this other example, it's we have put a virtual environment, which is a box. Basically, you can freely move the interface inside the box. And you see, I hope you see on the video that when you reach the limit of the box, you are really you are really blocked. Unfortunately, the video seems to be slow, but maybe if you want, I can show you on my computer. It's not that slow in reality, but you really have the feeling of a haptic device. Okay, so in conclusion, so this work showed that we are able to build a new haptic device made of a deformable structure. So of course, it's this device is when you compare to doing a real haptic device, articulated rigid body approach, it's much easier to build a deformable one. There is no slack, no friction. So today the model is only based on static analysis. So the future work will investigate really a dynamic approach, in particular to evaluate with model analysis what are the natural vibration of the device, and probably to put a design where we put the natural vibration of the device outside of the range of the vibration we want to emulate with the haptic device. And I think the main thing of this work is to show that structural mechanics like FEM model, etc., can be used for kinesthetic control of soft robots. So there will be a demo session on Wednesday of the team. So I really invite you to attend this demo session and see the demo of Defrost team. As he is here, so you will. So some of the work will be shown on Wednesday. What this work is available in open source in a SOFA framework. We have developed a consortium around this work, and there is a growing community of people using our software. And we are also developing new class on SOFA related to contact mechanics or non-linear deformation or even soft robots. So if you are interested, don't hesitate to contact the consortium. And just in a few slides, we are creating a new company, Compliance Robotics, where basically we will develop some teach class for soft robotics and to use like this type of modeling for building robots. So basically the robot, it's a little bit like the robot I showed you, but with only 4 motors. And basically you can adapt, you can put it in 2 configurations, either like that, it could be used as a device, or haptic device, for instance, or in this configuration, it's more to apply pick and place. Basically, yeah, we are developing a class on this, so the product will be available on September. So if you are interested, don't hesitate to discuss with me after this session. Thank you.
That work? Yes. Thank you very much for the nice talk. Is there any question in the audience?
Really great work. So in compliance structures, usually when you try to control them, you encounter bias stabilities or some singularities in the structures. So in your model, can you handle those kind of things and you can control?
That's a very good question. So basically, we can with the model we can predict when we arrive at instability, because in fact what's happening, for instance, with the compliance, if you take the very simple instability to understand, it's a beam where you push on the 2 parts, on the 2 opposite parts, right? And basically in such a case, you see that the force you apply creates a displacement, right? So when you are at the limit, you see in this W matrix a change in direction, because you can go from a direction where you push and it goes up, and from another direction where it goes down. So you see that there are some instability that appears so you can predict through the model, but it doesn't mean that we are able to. It's another problem to stabilize and be sure that with your feedback, you're really safe. So the way we do, so for instance, what we did with the robot I showed, the haptic device, is that we pre-curve, in fact, the beams to avoid this problem of instability and to be sure that in the workspace, we will not go from one position to the other, right? So yeah, but it's true that it's a very nice, I mean, a trend of research, I think, because there is a lot to explore on this.
Another question, maybe? Yeah.
Thank you for the talk. Very interesting. I just, this is not my area, so I was coming at it from a different point of view, and I was wondering is it possible to learn a mapping or a relationship, I don't know, maybe through a neural network that takes the servo motor positions directly to the position of the end effector? And that's something that you just learn by driving to every possible configuration.
Actually, very nice question, because actually a lot of people try to do that. But I think learning a mapping from position of the actuator to the end effector position is really a way of thinking in rigid robotics. Okay, it's because in rigid robotics, when you have a position of the articulator, you have a unique position of your end effector. But it's not true in soft robotics, right? Because in fact, there is a possibility of deformation that you cannot really know. But what we did, actually, we showed that instead of learning this mapping position, it's much more efficient to learn the compliance matrix, which is also a very small matrix. And so recently we did some work where basically based on the configuration of the actuator and the configuration of the end effector position, we learn, instead of computing the compliance matrix to DFEM model, we use the compliance matrix that has been learned in a pre-process. And it's much more efficient than learning just the kinematics, like the position to position, because you can really reproduce the fact that the user is applying some force, so it creates some deformation. My point about that is that, of course, we can do fantastic things with learning, but it's better to have an idea of the type of model we want, in fact, and the modeling can help, I think, on understanding what type of term we need to learn.
You have time for one more question. There's any? Yeah.
I wanted to ask you to comment a bit on the, like, when you stay in the box, right? When you showed the haptic experiment and you have your yellow environment, how is it working how can you really limit? Because when things are rigid, that's easy to imagine. In this case, I can understand you can apply forces, but how can you actually make sure that those forces result in a position that has been constrained?
Thank you for the question. So basically, in fact, when you go outside the box, you are more in this configuration. In this case, so we can basically measure the fact that you are outside the box, and what we ask to the robot in terms of control is to move the handle inside the box. Okay, so basically you will of course it will go against you till you are inside the box. And one of the things which is difficult which is interesting is that when we see the curve, of course it takes sometimes some iteration, but in fact the structure deforms, and the wall you emulate with this device is greater than the natural stiffness of the device. So if you block the motor, you obtain a certain stiffness, but the fact that we are able we measure the force, we act against the force, so the structure deforms, and at the end, the impression you have is a wall that is stiffer than the natural stiffness of the device.